Imagine if, like, every time you stubbed your toe, your foot wasn't allowed to just instinctively pull away.
Oh, that sounds awful.
Right. Imagine if instead your foot had to, draft a detailed email describing the impact, the exact angle of the coffee table, the intensity of the pressure.
Just a full incident report.
Exactly. And then it had to send that email all the way up your spinal cord to your brain, and your foot just had to sit there, crushed against the wood, waiting for your brain to read the message, process the data, and send an email back down, giving your muscles official permission to flinch.
I mean, you would probably bleed out or at least break a lot more bones before your body ever even realized it was injured. The latency alone would be completely crippling.
It would. It sounds like a totally absurd, darkly comic way to design a living organism.
Yeah, completely dysfunctional.
And yet, that absurd, crippling delay is, well, it's almost exactly how we are currently building the nervous system of the modern world.
It really is.
That is exactly how our artificial intelligence currently operates. So, welcome to a special deep dive, acting as our second installment of Innovation Toronto, The Edge.
It is so great to be here for this one.
Today, we are really slowing things down. We are stepping away from the frantic daily hype cycle of the tech industry, and we're going to take a very unhurried, deeply reflective walk through a monumental shift in how artificial intelligence works.
Because what we are looking at today is, it's not just a faster chip.
Right.
It is a complete reimagining of what intelligence looks like, and honestly, more importantly, what it feels like for you to live alongside it.
And that reimagining is not just a luxury, right? It's an absolute necessity.
Oh, 100%.
Yeah.
If we continue to scale up our current model of AI, which is essentially that toe-stubbing email system we just talked about, but on a global scale, we are going to hit an insurmountable wall.
A huge wall.
We are hitting an energy wall, a latency wall, and frankly, a deeply profound philosophical wall. The shift we are unpacking today is really about moving from an architecture of centralized control to an architecture of ambient presence.
So to guide us through this, we are pulling from two truly fascinating sources today.
Very dense, but fascinating.
Yes, very. The first is a groundbreaking, highly technical paper published recently in the journal Nature Electronics, authored by a team of researchers at Nanjing University, and it is titled Communication-Aware In-Memory Wireless Neural Networks.
I know, it is a spectacularly dense title.
It's a mouthful.
It is,
Yeah.
but I promise, every single hyphenated word in that phrase represents the shattering of a massive decades-old boundary in computer engineering.
And we are going to break all of that down until it makes perfect sense to you. Our second source is an accompanying analytical text called The Silicon Nervous System, The Rise of Distributed Intelligence.
Which is where the philosophy really comes in.
Exactly. Our mission for this deep dive is to explore both the mechanics and the profound meaning of this breakthrough. First, we are going to get into the hardcore engineering of, the edge.
Right.
We really need to unpack how this new technology from Nanjing University manages to reduce the power consumption of artificial intelligence by a staggering 95%.
Which, I mean, that is a number that should make anyone, whether you're a computer scientist or just someone who pays a monthly electric bill, stop dead in their tracks.
95% is just wild.
A 95% reduction is not a minor optimization. It is an evolutionary leap.
So we are definitely going to figure out the how of that 95%, but then we are going to spend the majority of our time exploring the massive philosophical shift that this hardware breakthrough creates.
Because the hardware actually changes the dynamic.
It does. Because when you change the physical location of where a computer thinks, you fundamentally change humanity's psychological relationship to the machine.
Right.
We are talking about moving away from this creeping existential dread of a centralized oracle in the cloud, this giant digital dictator we all fear is going to replace us, and moving towards something surprisingly beautiful.
It really is a beautiful vision.
The reality of a quiet, relational ecology of intelligence that we inhabit, rather than a machine we just serve.
And that's the most compelling part of this entire discussion for me. The hardware is literally leading the philosophy. By redesigning the silicon, we are, in a very real sense, redesigning our future alongside it.
So to fully appreciate the elegance of the solution, we have to really feel the pain of the problem first.
We have to look at the bottleneck.
Right, the bottleneck of our current paradigm. Let's look at the physical reality of what happens when you interact with a smart device today. We live in a world filled with what engineers call edge devices.
Right, and the edge simply means the very outer perimeter of the digital network.
The fringes.
Exactly, the place where the internet actually touches the physical, messy, real world. Your smartphone is an edge device.
The smart thermostat on your living room wall.
Yep, the cameras on an autonomous vehicle looking for pedestrians. The tiny moisture sensors buried in the soil of an agricultural field. They are basically the sensory organs of the internet.
But here's the massive catch. These sensory organs are generally starved for energy.
Totally starved.
Your phone relies on a lithium-ion battery. That field sensor might be surviving on a tiny, dusty solar panel. A smartwatch is running on a battery the size of a coin.
Right. They do not have the power reserves, the thermal cooling, or even the physical real estate to house giant, complex artificial intelligence models.
So when they need to do something highly complex, say, your smart speaker needs to parse the nuances of human speech, or a factory sensor needs to analyze a high-resolution vibration pattern to predict if a turbine is about to explode. They can't do the heavy intellectual lifting themselves.
They simply don't have the biological, or rather the silicon capacity.
So they have to ask for help.
They have to call the boss. They have to take all that raw, heavy data and transmit it over a wireless network, Wi-Fi, 5G, whatever's available, and blast it all the way up to the cloud.
And the cloud, as we all know, is not actually a fluffy cloud.
No, not at all.
It's a massive, windowless, hyper-cooled data center sitting out in the desert or next to a hydroelectric dam, just packed with thousands of power-hungry servers.
Exactly. The cloud does the heavy thinking, figures out the answer, and then transmits the result all the way back down to the edge device.
And that round trip, that massive, invisible logistical migration of data is the exact bottleneck that is currently choking the AI industry.
It really is. And the sources we are looking at identify three major points of separation in this current setup. Three distinct boundaries that cause this crippling latency and a wildly unsustainable drain on our energy grids.
Let's list those out.
First, you have the separation of memory and computing inside the device itself. Second, you have the separation of signal processing and transmission. And third, the separation of the neural network's brain from the reality of the wireless communication channel it relies on.
Okay, those three separations sound incredibly abstract, so I want to frame this in a way that makes the physical inefficiency crystal clear for you listening.
An analogy is definitely needed here.
Let's imagine our current AI architecture as a highly dysfunctional, intensely bureaucratic corporate committee trying to solve a time-sensitive problem.
Well, we all have entirely too much experience with dysfunctional committees, so this is the perfect lens.
Right. So imagine you need this committee to solve a complex math problem. But the person who holds all the historical files, the reference books, and the raw data that's the memory is located in an entirely different building from the person who actually does the high-level math and analysis.
And that person is the processor.
Yes, the processor. So every single time the math person needs a new number to add to the equation, a courier has to sprint across the courtyard to the archive building, get the file, and run it back.
Exhausting just to think about.
That is your first separation, memory and computing.
Yeah.
In computer science, this is actually known as the von Neumann bottleneck.
And it is a bottleneck that has plagued computing since the architecture was invented in the 1940s.
Wow, that long.
Yeah. The central processing unit, the CPU, is incredibly fast. But it is constantly starved for data because it has to wait for those tiny digital couriers to fetch information from the RAM, the memory.
Right.
And every time that courier runs across the microscopic wires of the motherboard, it generates heat and it consumes electrical power.
Exactly. The processor is basically just sitting there twiddling its thumbs, burning electricity, waiting for the file to arrive.
Yep.
But in our corporate committee, it gets even worse. Once the math person finally gets the data and does the calculation, they can't just shout the answer out the window.
No, that would be too easy.
Right. They have to hand their written result off to a translator, the signal processor, who turns the mathematical answer into a specific communicable code. Then that translator has to run down the hall and hand it to a guy holding a massive megaphone, and he's the radio transmitter.
That is your second separation, the separation of signal processing and transmission.
Right.
In a standard device, these are literally different chips, or at least highly distinct components on a circuit board, all requiring their own dedicated power sources and energy just to hand the data off from one to the next.
And finally, we hit the third and honestly most frustrating separation. The guy with the megaphone has to shout these translated findings over a crackly, wind-blown, interference-filled courtyard to a distant, incredibly demanding boss sitting in a skyscraper miles away.
The cloud server.
The cloud server. And here is the kicker. The boss's brain, the neural network, is completely isolated from the reality of the megaphone guy.
Completely blind to it.
The boss just demands the data, regardless of whether it's raining or there are sirens going off or the megaphone is running out of batteries. The boss doesn't care about the medium. He just wants the message. That is the separation of the neural network and the wireless communication.
It is a brilliant analogy because it really highlights the absurdity of the energy distribution here.
Right.
If you look at that entire corporate process, the actual work, the moments where the math person is actually crunching the numbers, is only taking up a microscopic fraction of the company's time and budget.
Almost none of it.
The vast, overwhelming majority of the company's resources, its budget, its literal calories, are being spent entirely on logistics, just weaving the information around.
The courier sprinting across the courtyard,
Yeah.
translator running down the hall, the guy shouting until his lungs give out.
Precisely. In modern computing, the energy spent just moving data from the memory chip to the processor, and then moving that processed data from the antenna up to the cellular tower and into the cloud, absolutely dwarfs the energy spent actually computing the data.
It's all in the movement.
The data movement is the primary source of power consumption and battery drain.
So we have this massive, invisible logistical nightmare happening thousands of times a second.
Yeah.
Every time you ask your smart speaker to turn on the lights, your voice is packetized, sent to a router, routed under the ocean or across the country to a data center, processed, and a command is sent all the way back just to flip a switch 3 feet away from you.
It's wildly inefficient.
Which brings us to the massive pivot point of today's deep dive. If moving the data is the core problem, if the courier running between buildings is exhausting all our power, how do we fundamentally redesign the hardware so that the thinking happens exactly where the data already lives?
And this is where we dive into the technological leap and that fascinating paper from Nanjing University. Because to solve a deeply entrenched 80-year-old architectural problem, the researchers didn't just try to build a faster courier.
Right.
They didn't just try to make the megaphone louder. They decided to demolish the separate buildings entirely.
Communication-aware, in-memory, wireless neural networks. We promised to demystify this, so let's get into the actual mechanics. How on earth do you demolish those buildings?
Let's start with the middle part of that phrase.
Mm-hmm.
In-memory computing, specifically analog in-memory computing.
Okay.
As we established, traditionally, memory chips are just dumb storage lockers. They hold data, and processing chips crunch data.
Right.
In-memory computing essentially gives the memory chips the ability to do the math themselves right in the locker, right where the data is already sitting.
So going back to our committee, you are handing a high-powered calculator to the archivist sitting in the file room. You fire the courier entirely.
Exactly. But how they do it is the real magic here. They do it in an analog way.
Analog.
Yeah. Now, we are so used to the digital world that we kind of forget what analog actually means. Digital computing uses binary logic, rigid absolute zeros and ones. Transistors acting as tiny on or off switches.
Right, ones and zeros.
Analog computing uses continuous physical properties. Think of digital as a light switch. It's either completely on or completely off. Analog is a dimmer switch. It can be anywhere along a continuous spectrum.
Okay, so how does a dimmer switch do complex artificial intelligence math? That's the part I'm struggling with.
It comes down to the fundamental math of neural networks. Artificial neural networks, which are loosely inspired by the human brain, rely on billions of mathematical operations called multiply and accumulate operations.
Multiply and accumulate.
Right. You are constantly multiplying an input by weight and adding it to a running total. It turns out, if you design specialized analog memory materials like a grid of memristors or phase change memory, you don't need a digital processor to do that math. You can just use basic high school physics.
Really?
Yeah. Ohm's law.
Wait, Ohm's law, like voltage, current, and resistance.
Yes. V equals I times R. Or if we look at conductance, current equals voltage multiplied by conductance. So the researchers apply a specific voltage to a wire. That voltage represents the input data.
Yeah.
The physical electrical resistance of the memory material itself acts as the mathematical weight of the neural network.
Oh, wow.
As the electricity naturally flows through the material, the physics of the circuit automatically multiplies the voltage by the conductance, producing a current. And because these memory grids are built in massive crossbar arrays, the currents naturally add together at the end of the wire.
Okay, let me make sure I am fully grasping this because it's wild. You are saying they aren't writing a software program that says multiply 5 by 4.
Yeah.
They are just shooting a specific amount of electricity through a physical material that has a specific level of resistance, and the resulting electrical current actually is the mathematical answer.
Yes, exactly. The physics of the material naturally, instantly computes the math. Thousands, millions of operations simultaneously, simply by letting electricity flow through the grid.
That is unbelievable.
No couriers, no digital logic gates. It happens at the speed of electricity, with a microscopic fraction of the power required by a digital processor.
Okay, my mind is genuinely blown by that. You are using the raw physical properties of the universe to do the math, rather than running a rigid software algorithm.
It's elegant.
It's beautiful, but the Nanjing University breakthrough goes even further than that. The paper states that this architecture dissolves the boundaries among memory, computation, signal processing, and communication into a single AI-powered system.
And this is where it elevates from a clever hardware trick to a truly revolutionary paradigm shift.
Yeah.
They didn't just put the calculator in the file room with the archivist. They took the translator and the guy with the megaphone, and they shoved them into the file room too. And then they melted them all together into one unified, singular entity.
I want to focus deeply on this specific detail from the sources because it genuinely made me stop reading and stare at the wall for a minute.
It's a heavy concept.
The paper says that wireless communication is integrated as a learnable module of the wireless neural network itself.
Right.
This broke my brain a little bit. Are they saying that the antenna, the radio, and the AI's brain are no longer different components? The physical act of communicating over radio waves is literally part of the AI's learning process.
Yes. And your reaction is completely justified. This is a profound conceptual shift.
Okay, explain this to me.
Let's go back to the old paradigm of the guy with the megaphone. In traditional systems, the AI model in the edge device makes a calculation. It spits out a string of digital zeros and ones. It hands those numbers to a separate radio transmitter, the megaphone guy.
Right.
And the transmitter's only job is to blindly blast those numbers out into the airwaves as best it can, using a rigid, pre-programmed protocol. The AI brain doesn't know or care about the radio waves. It doesn't know if there is static or if it's raining or if there is a massive steel wall blocking the signal.
Right. The boss doesn't care about the crackly radio. He just wants the number sent, and if the transmission fails, the radio just tries again, burning more battery.
Exactly. But in this new Nanjing architecture, the wireless transmission is not a separate, blind, dumb pipe. The physical act of modulating the radio signal is deeply embedded within the neural network's architecture.
As aware of it.
The AI is communication aware. It actively perceives and understands the state of the wireless channel. It understands the static, the multipath interference bouncing off buildings, the distance to the receiver.
Wow.
And because it's a learnable module, the neural network adjusts its own internal parameters, its own thoughts, essentially to optimize how the information physically travels through the air.
So it's not just thinking about the data itself, it's actively thinking about how to shape its thoughts so they perfectly ride the specific radio waves available in that exact millisecond.
Beautifully put. The medium becomes part of the cognition. The AI isn't just sending data over a radio. The radio transmission is fundamentally part of its cognitive process. It learns how to communicate efficiently through a noisy environment in the exact same way. It learns how to recognize the image of a cat or predict a temperature fluctuation. It weights the importance of the data and dynamically adjusts the radio modulation to ensure the most critical insights punch through the noise while letting less important data drop away to save power.
That is just... it's like discovering a new biological sense.
It really is.
It's like if humans suddenly evolved the ability to instinctively adjust the physical shape of our vocal cords based on the real-time acoustic properties of the room we're standing in, so our whisper could perfectly bounce off the walls and reach someone 100 feet away without anyone else hearing it.
Oh, that's a great way to think about it.
We wouldn't just be choosing our words, we'd be consciously manipulating the physics of sound.
That is a phenomenal analogy. It represents a level of holistic, organic integration that traditional computer engineering, which loves to build separate, modular, rigid boxes for everything, rarely achieves. It's moving away from building machines like factories and closer to building them like organisms.
Okay, so we have this beautifully elegant theoretical model. We've collapsed the boundaries between memory, computation, and the radio itself using analog physics.
Right.
But theory is one thing. What happens when we expose this delicate, highly unified analog system to the messy, chaotic reality of the physical world? We need to look at the experimental results. Because a lab experiment is easy, the real world is hard.
The transition from theory to a physical prototype is always the crucible for these technologies. And the real-world prototype results from the Nanjing team are what elevated this from a neat idea to a Nature Electronics publication.
So the text highlights that the experimental results show an inference accuracy of 93.71%.
Right.
Now, for you listening who maybe isn't deeply embedded in machine learning metrics, 93.71% sounds pretty good, like a solid A- on a test. But given the radically new analog architecture we just described, how impressive is that number in context?
In context, it is remarkably impressive. You have to remember, analog computing is inherently noisy.
Because it's a dimmer switch, not a rigid on-off.
Exactly. When you use continuous voltages instead of rigid digital ones and zeros, there's natural variation. If the temperature of the room changes by a few degrees, the electrical resistance of the material changes slightly. Tiny manufacturing imperfections in the crossbar array introduce variance.
That makes sense.
So to achieve nearly 94% accuracy in complex inference tasks on a completely new analog and memory architecture proves that the system is not just a delicate, finicky lab experiment. It is robust. It can handle the intrinsic messiness of the physical world.
And speaking of robust, the sources heavily highlight the system's resilience to external chaos. It says the neural network can actively adapt to fluctuating environmental variables, specifically signal fading and interference.
This circles back perfectly to our discussion of the communication-aware learnable module. In the real world, signal fading is a constant nightmare.
I can imagine.
Think of a factory floor filled with moving metal robots bouncing Wi-Fi signals in random directions, or a smart agricultural field where heavy rain, wind, and sheer distance actively degrade the radio signal. Because the neural network is actively learning and adapting to the state of the communication channel in real time, it doesn't need pristine, perfect lab conditions to think clearly. It senses the interference. It senses the fading.
And it adjusts.
And it dynamically adjusts its transmission strategy, shifting its power to punch the most important data through the noise.
It's street smart. It's not a pampered, delicate AI that throws an error code the second it doesn't have a perfect, uninterrupted fiber optic cable connection.
Exactly. It is designed from the ground up for the unpredictable reality of the physical edge.
But here is the big reveal. This is the metric that justifies everything we are talking about today. The integrated system reduces the wireless transmission power required for collaborative inference tasks between a terminal device and a cloud server by up to 95%.
Yep.
95%. Let's just sit with that for a second.
It's a staggering figure. When you optimize the entire stack, doing the heavy math right inside the memory using the low-power physics of analog materials and having the AI actively, intelligently optimize its own radio waves, you strip away all the wasted logistical energy.
All the running back and forth.
You finally eliminate the courier running across the courtyard, you fire the translator, you take the megaphone away.
I really want to drill down into the so what of this 95% reduction. Because it's so easy for us to hear a stat like that and just think, oh, cool, my Apple Watch battery will last a week instead of a day.
Which would be nice. But
it's so much bigger than consumer convenience, right?
Yeah.
What happens to the world when the power cost of intelligence drops by 95%?
If we pull back and look at the macro picture, it fundamentally alters the scaling laws and the environmental trajectory of artificial intelligence.
How so?
Right now, the global AI boom is creating a literal energy crisis. We are building massive, centralized cloud data centers that consume as much electricity as small European countries.
It's terrifying when you read those stats.
They require millions of gallons of fresh water every single day just for cooling. Tech companies are desperately trying to reopen decommissioned nuclear power plants just to feed these servers. We're trying to brute force our way to advanced intelligence by burning massive amounts of energy.
It's the brute force approach of the centralized factory boss. Just throw more coal in the furnace.
Yes. But if you drop the power requirement by 95% at the edge of the network, you break that dependency.
Wow.
By minimizing the need for costly, constant data exchanges through efficient in-memory computations, AI can now operate sustainably and responsively right on the edge nodes. The local sensors, the smart urban environments, the autonomous vehicles, the medical implants, they don't have to constantly phone home to the massive centralized cloud data centers to understand their world.
They can think for themselves.
They can think for themselves locally, efficiently, using milliwatts of ambient power instead of megawatts of grid power. We unchain AI from the centralized server farm.
Okay, so we've established the mechanics. We've established that AI no longer requires a massive, distant, power-hungry facility to function. It can live right here, right next to us, woven into the fabric of our lives efficiently at the edge.
Yes.
But here is where we hit the crux of our deep dive. Because changing where the computer thinks entirely changes how we feel about the computer.
This is the philosophy.
Right. As you unchain the AI from the data center, you force us to confront a massive psychological complex we have about artificial intelligence.
And this is a crucial pivot. Because our societal anxieties about technology are almost always direct reflections of the architecture we use to build it.
Exactly. I want to shift our tone here, moving away from the highly technical engineering of memory arrays and radio frequencies and wade into something deeply human.
Let's do it.
Let's talk about how human society currently views AI. If you read the news, if you watch science fiction movies, we view AI almost entirely through a lens of fear and centralized control.
The analytical text we are referencing, the silicon nervous system, calls this the fear of the replacement CEO, or the oracle in the cloud.
The oracle in the cloud. I love that phrasing so much because it captures both the religious awe and the absolute terror we project onto these big language models right now.
It really does.
Because we currently build AI as a massive centralized decision machine housed in a billion-dollar facility guarded by biometric security, we naturally fear that it will eventually act like a supreme dictator. We fear it will replace human judgment entirely.
And it raises a profoundly important question. Why do we assume that superintelligence must inherently be dictatorial?
Right.
It's because we have mapped our own flawed human power structures onto our silicon creations. We think of intelligence purely as a top-down command and control function. If there's a very smart brain in the room, human history tells us that brain usually ends up in charge, telling all the less smart things what to do.
And the psychological extrapolation of that fear is fascinating. The source text touches on this specific anxiety. It's not just the Hollywood fear of the Terminator of being violently wiped out by robots. It's a quieter, perhaps much more insidious fear. The fear that humans will atrophy.
The fear of becoming obsolete.
Oh.
Not destroyed, but entirely sidelined.
Right. If the oracle in the cloud makes all the best decisions, if it flawlessly optimizes our global economy, routes our traffic with zero accidents, diagnoses our medical conditions better than any doctor, and drafts our legal contracts perfectly, what do we do?
That's our purpose.
Exactly. We fear shifting from being the active creators of our world, the messy, mistake-making authors of our own destiny, to becoming mere supervisors. We picture ourselves just standing around with clipboards, watching the dials of an alien system that we don't really understand, desperately hoping it continues to decide to keep us comfortable.
It is ultimately the fear of losing our dominion over the physical world. We have spent thousands of years mastering our environment through our own intellect and our own hands. To hand that mastery over to a centralized artificial intellect feels like a profound evolutionary surrender. It feels like we are retiring as a species.
And I think we all feel this on some level. Think about how you feel when you scroll through your feed and read those headlines. You read that a new AI model has passed the bar exam in the 90th percentile, or that a single AI data center in a small town is using more water than the entire local municipality.
It's intimidating.
It naturally feels threatening. It doesn't feel like a helpful tool you are holding. It feels like an imposition looming over you. It feels like we are actively, willingly choosing to build a digital dictator, and we're just crossing our fingers and hoping it turns out to be a benevolent one.
It frames the future as a zero-sum game. The smarter and more capable the centralized AI gets, the less agency and purpose the human has.
But what if this terrifying centralized monolith isn't the final form of AI at all? What if this massive, power-hungry oracle in the cloud is just technology's awkward adolescence?
Now that is the insight that changes everything.
Let's look at the counter-argument presented in our text, which explores the true geometry of intelligence and the concept of the silicon nervous system. Because the text argues that the fear of the replacement CEO completely misunderstands how deep intelligence actually works in the natural world.
What's fascinating here is stepping entirely outside of computer science and looking at biology. Biology has been doing highly complex information processing for billions of years.
Right.
And biology almost never relies on a single, massive, centralized dictator to run a complex dynamic system.
The text argues that intelligence naturally wants to distribute itself. It wants to be local.
Absolutely. When we look at advanced biological systems like a human being, yes, there is a brain. But the brain isn't micromanaging every single function of the body. By pushing memory and processing to the edge, which is exactly what this Nanjing University breakthrough allows us to do with near zero energy cost, we are actually mimicking biology.
Yeah, we're growing up.
Yes, we are watching technology evolve out of its awkward, highly centralized adolescence. We are not building a giant metallic CEO to boss us around. We are building a silicon nervous system.
The text uses a biological analogy here that genuinely shifted my perspective. It compares our current cloud-based AI setup to a human body that lacks a local immune system. I want to spend some time unpacking the Papercut analogy because this is the absolute aha moment of the whole deep dive for me.
It's a great one. Let's talk about skin cells.
Let's do it.
Let's consider a very mundane, everyday event. You're opening a cardboard package and you get a paper cut on your index finger. All right. Now, in the centralized Oracle in the cloud model of computing, here is how your body would have to react. The injured tissue in your finger would have to compile a massive data report describing the exact nature of the laceration, the depth of the cut, the ambient temperature of the room, the specific microscopic bacteria present on the cardboard.
A full incident report like the toe-stubbing.
Exactly. It would have to send all that raw, heavy data up the network of your spinal cord to the centralized cloud server of your brain. The brain would have to stop whatever higher level thinking it was doing, stop thinking about this deep dive, stop regulating your breathing, stop maintaining your balance just to process the Papercut data.
That sounds horrible.
The brain would calculate the exact immune response needed and then send a command signal back down the arm to the finger, telling the specific local cells to begin clotting.
Which, when you describe it biologically like that, sounds absurdly slow, inefficient, and dangerous. You'd bleed out from a minor scrape before the brain ever finished processing the data and sending the command.
Yeah, exactly. It's the von Neumann bottleneck, but applied to human biology. But obviously, that is not how your body works. Your skin cells do not ask the brain for permission to heal a paper cut.
They just handle it.
They communicate locally. When the tissue is damaged, the cells immediately release chemical signals, histamines, cytokines. The local blood vessels instantly recognize those specific signals and dilate. Local platelets immediately begin to aggregate and clot to stop the bleeding.
Wow.
The white blood cells that are already patrolling that specific area rush in to fight potential infection.
The intelligence is distributed.
The intelligence is hyperlocal. The skin cells and the local immune system are using their own localized intelligence to solve the problem immediately, right where the physical injury occurred. Now, the brain is eventually notified. You feel the sensation of pain. You cut yourself. But the brain doesn't have to manage the granular, microscopic logistics, the healing process. The edge nodes handle it autonomously.
Okay, let's extrapolate that and apply it to the manufactured world we are building. Because viewing technology through the lens of a local immune system completely shifts how I view the smart devices around me.
With the kind of ultra-low power, communication-aware edge computing we've been discussing, where the intelligence is baked right into the memory of the device itself. Our devices, our rooms, our urban environments can act exactly like those biological skin cells.
So imagine an autonomous car hits an unexpected patch of black ice. In the old paradigm, it has to send sensor data to a cloud server to ask a centralized AI how to correct the steering. But with this new paradigm, the sensors on the tires themselves have the localized intelligence, the analog and memory neural networks, to instantly calculate the friction loss and adjust the microbraking independently in a millisecond without ever talking to the cloud.
Yes. Or consider a smart energy grid. A local transformer detects a sudden massive surge in demand on a specific city block because everyone turned on their air conditioning at the exact same time. It doesn't need to wait for the central municipal command center to balance the load. It negotiates directly, peer-to-peer, with the solar panels and home battery storage units on that specific street to smooth out the power delivery instantly, preventing a blackout.
It's handling its own localized issues intelligently without reporting back to the boss. But let me push back on this for a second because my mind immediately goes to the potential chaos of this.
Okay, what's the concern?
If everything is localized, isn't that inherently unstable?
Right.
If a skin cell goes rogue and stops communicating with the whole, biology calls that cancer.
Right.
If a smart traffic light or a localized power node goes rogue and stops listening to the central system, couldn't that cause a massive pileup or grid collapse? Doesn't decentralization invite a massive security and coordination nightmare?
That is a phenomenal question, and it's the exact challenge engineers face when moving from a centralized to a distributed system. But the key here is that decentralized does not mean disconnected. Remember the Nanjing paper. These are communication-aware neural networks. They are constantly maintaining a web of relational awareness with the nodes around them. In a biological system, cells rely on local consensus. If one cell starts acting erratically, the surrounding immune cells recognize the anomaly and neutralize it.
So the network polices itself.
Yes. In a silicon nervous system, edge nodes use peer-to-peer consensus algorithms. If a traffic light sensor locally decides to turn green when the surrounding sensors know cars are coming, the local network consensus overrides the rogue node instantly. The intelligence isn't isolated. It is woven into a local fabric that is constantly checking its own equilibrium.
So the local nodes act as a check and balance on each other without needing the centralized cloud to police them.
Exactly. They form a resilient nervous system that reflexes, adapts, and corrects itself at the speed of the physical world, not the delayed speed of a distant cloud server.
If the world around us is truly filled with these tiny, autonomous, hyper-efficient nodes of intelligence checking and balancing each other, our fundamental relationship with technology transforms.
It really does.
It's no longer a glowing screen we stare at, or a master we serve. Which brings us to our final point, inhabiting an ambient ecology.
This is where we reach the beautiful philosophical conclusion of our deep dive. When you distribute intelligence so thoroughly, so quietly, and so efficiently into the very fabric of the physical world, it ceases to feel like a machine.
The source text says that edge computing turns AI from a tool we must consult into an ambient ecology we inhabit.
Think deeply about the word ecology. A forest is an ecology. A coral reef is an ecology. There is immense, staggering intelligence in a forest. The complex way trees communicate threats and share nutrients through underground fungal networks, the way the entire ecosystem balances its predator and prey dynamics, the way it responds to rainfall.
Yeah.
But you don't walk into an old-growth forest and feel like you are being commanded by a central computer. You don't feel subjugated by the trees.
You feel surrounded by a living, breathing system. You feel a sense of belonging, not a sense of being managed.
Yes. The text uses a beautiful phrase, intelligence becomes relational. When artificial intelligence is decentralized and embedded natively in the environment via these microscopic low-power analog nodes, it isn't a singular monolithic entity we have to ask for answers.
Right.
It pulses quietly in the space between the nodes. It responds to our presence. It adapts to our needs. It maintains the physical equilibrium of the environment.
I want to focus on this idea of profound comfort, because the text concludes with a thought that acts as a total antidote to the anxiety we discussed earlier. It says, "We are not merging with the machine, and the machine is not conquering us. We are simply meeting it in the environment. It is a partnership, not a subjugation."
This directly addresses that deep-seated fear of human atrophy. If AI becomes an ambient ecology, it doesn't replace us any more than nature replaces us. A forest doesn't replace you, it supports you. It provides the oxygen you breathe, the shelter you use, a context for your physical existence.
Wow. Yeah.
If our smart buildings dynamically manage their own energy efficiency without our input, if our transit systems locally route around congestion to keep the city flowing, if our medical sensors quietly monitor our baselines and heal small anomalies without demanding our constant panicked attention, they are freeing us. They are handling the metabolic logistical functions of our civilization exactly like your autonomic nervous system handles your breathing and your heart rate without you having to consciously think about it.
So that our conscious minds are finally free. If the machines handle the metabolic logistics, human beings are free to do what only human beings can do. Art, philosophy, connection, emotional creation.
Exactly. It's a true partnership where the silicon nervous system handles the complex, high-speed, invisible logistics of the physical world, allowing human judgment, human nuance, and human creativity to flourish at the macro level. It is the exact polar opposite of the digital dictator.
I am reflecting on how incredibly peaceful this vision is compared to the sci-fi dystopias we have been force-fed for decades.
Oh, absolutely.
When we imagine the future of advanced AI, it's always neon lights, giant holographic screens, and a booming metallic voice barking orders from a glowing red eye. But the true future of advanced AI, driven by the kind of brilliant hardware breakthroughs we've seen from Nanjing University, might actually look entirely invisible.
Completely invisible.
It's not a giant metallic CEO. It's a quiet, responsive forest of intelligence. It's a room that perfectly adjusts to the sunlight, a bridge that intuitively knows where its own structural fatigue is and calls for repair, a world that just works softly, intelligently.
It is the ultimate triumph of technology. The truest mark of advanced technology is not how loud it is or how much it demands our attention. The ultimate triumph is for technology to become so perfectly integrated, so hyper-efficient, and so deeply relational that it essentially disappears completely into the background of our lives.
What an incredible journey this has been. Let's take a moment to recap the massive territory we've covered today.
We covered a lot of ground.
We really did. We started with a highly technical, physically frustrating hardware bottleneck, the von Neumann architecture, the energy-draining separation of memory, computing, and wireless communication. We looked at how our current systems force massive amounts of data to travel to a centralized, power-hungry cloud just to do basic thinking, and how that is driving an unsustainable energy crisis.
And then we explored the physical breakthrough, the communication-aware, in-memory, wireless neural network. We saw how analog computing allows the memory materials to perform complex matrix math using the raw physics of electricity, and how integrating the radio transmitter as a learnable, adaptable part of the AI's brain collapses all those rigid boundaries into a single, elegant, organic system.
And the result of that elegance was that jaw-dropping metric, a 95% reduction in the power required for these tasks, even in noisy, chaotic, real-world environments. But as we discovered, that 95% power drop wasn't just a win for battery life. It was the catalyst for a total paradigm shift. Unchaining AI from massive data centers allows intelligence to truly decentralize.
Which allowed us to confront our deepest societal fears about AI. The fear of the centralized cloud oracle, the fear of the replacement CEO that will inevitably render humanity obsolete and atrophy our agency.
We realized that fear is based on a flawed, top-down human model of power. By looking at biology, by understanding that intelligence naturally wants to be local, like skin cells independently healing a papercut, we found the profound beauty of the silicon nervous system. We moved from the fear of subjugation to the peaceful vision of an ambient ecology, where intelligence is relational, quiet, and deeply supportive of human flourishing.
It is a profound, necessary shift from building tools of command and control to nurturing an environment of connection.
And so as we wrap up, we want to leave you with a final, provocative thought, something for you to ponder as you walk through your home or drive down the street or interact with the physical world today.
I love this part.
If our physical environments truly become saturated with this distributed, highly local skin cell intelligence, if the very materials of our rooms, our vehicles, and our tools can quietly adapt, learn, communicate, and heal themselves without ever needing instructions from a centralized brain, how will that change our fundamental definition of what is alive?
That is the question.
Will we, over the next few decades, eventually stop thinking of our technology as cold, manufactured, lifeless machines? And will we start treating our smart environments, our cities, and our homes as companion organisms in a shared living ecosystem?
A fascinating, beautiful question to take out into the world.
Thank you for taking this unhurried walk with us today. This has been the second installment of Innovation Toronto, The Edge. We'll see you in the deep end next time.